Tomorrow's announcement of to-do list is going to be extremely important for everybody to read. It will post either later this evening or first thing in the morning, way early in the morning. But it's going to be very critical for you guys to follow the directions on the announcement for tomorrow. You know, the plans for the day announcement I always put out there. The bottom line is tomorrow morning we will not be having an online conference. I'm going to let you guys get caught up on some book work. I'm going to let you guys get caught up on homework. And I'm going to have a few videos that I want you to watch. The reason for not having an online conference, quite honestly, is I have a bunch of meetings where I have to attend because we're trying to plan for getting you guys back on campus for labs. We don't know exactly how that's going to happen. Every state is different. I don't have answers right now for you, but we are in the planning stages of doing that, and I have to be involved in that process. I have too many programs I'm responsible for. So again, tomorrow's announcement for the plans for the day is going to be critical for everybody to look at. Does anybody have any questions? Okay. I hate doing that. I hate missing a day online with you guys. But I have to be involved in this planning process. I got to get that done. So please read that announcement. Don't miss anything on it. It's going to be a checklist of things I need you to do. Okay, moving on to today's topics. I want to talk about power distribution today. Okay, that's our subject of the day. We're going to talk about power distribution with respect to the incoming power. I'm going to talk a little bit about single phase. I'm going to talk about three phase. I'm going to talk about how breaker panels are set up. So that is our topic for today. Okay, because everything we do works on electricity. We got to get that electric from somewhere. Now in air conditioning, you're not only dealing with residential where we're dealing with small amounts of, and I consider 120 volts a small amount of power. Okay, others may disagree with me. But we're dealing with not only the small amount of power with 120 volts, but we could be dealing with 208. We could be dealing with 240. We could be dealing with 480 and even 720. So you got to be very aware of what you're reaching into, because those different voltages have different potential to actually reach out and get you. Has anybody here heard the term arc flash?
Yes.
Describe what an arc flash is to me if you've heard the terminology before. Go ahead and what is arc flash?
When a bolt of electricity jumps from a circuit to another metal object?
Yeah, it's basically the voltage is high enough on something and you have another metal object close enough, or a human object, which is what my bigger concern is, where the voltage is actually going to jump across the gap, and it's going to get you. I mean, people get killed by arc flash. So even though your screwdriver may be 12, 14 inches away from something, okay, you might still be got by that flash of power that's coming out. Okay, electricians have to go through arc flash training. And I think it's something that most people should do anyways. The NFPA, and I'm not advertising for them, but if anyone's interested in arc flash training, I'll throw a link up online. There's a short online training class where you can get certified in arc flash. I mean, it's like, I think it's a 20-hour video session, basically, where you can get certified in arc flash by the NFPA. And it opens up some doors to possible jobs like on public work sites for you guys. But the arc flash is a very important thing to keep in mind as we go through this. It's probably one of the most dangerous things that can happen in the HVAC industry. Does anybody here believe... Who was that?
I said Dylan, I've had it happen. Yeah.
What happened?
I had it happen. I was doing a commercial roofing job on McDonald's in Rhode Island, in Long Island, and the contractor, the foreman of the job, said that the power was dead on the roof, and we had to remove all these electrical wires that ran around the top of the roof. And I was using, thank God, insulated snips to cut these wires from these conduit boxes, and as I was cutting the one, it was still hot, and it arced and it welded the two blades of the snips together. That's how hot it was.
Did you smack the guy in the back of the head?
That's a very scary thing, Dylan. I mean, honestly, people are lucky to live through that. I lost the entire front 2 inches off a screwdriver once because of a similar situation. I was reaching into a piece of equipment to take a screw out. It wasn't even near anything hot. And again, honestly, it's my own fault. I should have checked. But I was with an apprentice, and I had told the apprentice to turn the power off. And the apprentice came back and told me, yep, he had turned the power off, and the guy had been with me as an apprentice for probably 1.5 years. So I had no reason not to believe him. Okay, again, my own fault. I should have checked. But thankfully, it was an insulated screwdriver, or the problem would have been much worse. It was 720 volts in a rooftop unit. Again, it took the front part of a screwdriver off on me. So I still have the screwdriver.
And you see it all, the flash. You see the electric moving.
Yes.
And when it blows a hole in a set of steel snips and welds the blades together, you know, it's powerful.
Yeah, this is probably one of the things that kills more HVAC technicians and more electrical workers than anything else. Okay, this is a real issue. In some of our labs on the campuses, and again, depended a lot on state rules, you will see that just about every disconnect is labeled for its arc flash potential. It might have like a category 1, category 2, and that all has to do with what type of personal protective equipment you should be wearing if you're working on that circuit live. If anybody ever wonders why we have locks all over some of our shops where the instructor's the only one that has the key, and we lock out these circuits, it's for this reason. We've fortunately never had an incident in our shops, but other schools have had major incidences in their HVAC shops, even on the arc flash. So we're extremely careful on this. And it will weld metal. It will knock holes in metal. And if it can weld a set of tin snips together or a set of lineman pliers, think about what it can actually do to you. So that's why we want to spend some time on power distribution, okay? Quite honestly, this is the first class I had that had somebody that this happened to in it, so that was interesting. Okay, so I want to talk, we're going to start by talking about power distribution. Now, I have a couple PowerPoints that I want to run through today. There's a couple slides in each of these PowerPoints that overlap with each other, but that's okay because they're relatively important for us to talk about and to think about. So, let's go ahead and we're going to start with some definitions. Okay, and these are sort of important. A single phase circuit. Okay, a single phase is an AC circuit with 2 current carrying legs. Now let's be very careful here, okay, because every circuit you come across will not have a neutral. Okay, neutral is, as I'll explain on a coming slide, neutral is something that's specific to a 120 volt circuit, okay? Once you get over 120 volt circuits, you're no longer going to have a neutral unless part of the appliance still uses 120 volts, okay? But most of our equipment is going to have an L1 and an L2 at a minimum. Once you get into commercial, we have 3-phase power. You don't see 3-phase power most often on residential. I don't want to say never, because there are a few houses that I went to in Massachusetts that do have 3-phase, but most often 3-phase is strictly for commercial. Okay, it's an AC circuit where there's 3 current carrying legs, all with electrical potential to ground. You'll see L1, L2, L3. So again, the difference is the number of current carrying legs with potential to ground. And again, neutral's a little weird, but in the reality, in a residential circuit, it is a current carrying leg. Okay, because it does return the current to the breaker panel and in turn to ground. The term hot conductor is any current carrying conductor that would show potential to ground. Let me repeat that again. Any current carrying conductor that shows potential to ground. Now, should neutral in a residential circuit, should neutral show a potential? In other words, if you put your voltmeter on neutral and put your voltmeter on ground, should we see any voltage?
No.
No. If we see voltage, there's a problem someplace with the power distribution. And I'll explain that more when we talk about breaker panels a little bit. But we should not see any voltage from neutral to ground. If we do, somebody has screwed up someplace. A ground conductor. It's a non-current carrying conductor connected to ground. It's colored green, or it's bare copper. Could be green insulated, or it's bare copper. Now, let's see who was paying attention yesterday. What is the G terminal on the thermostat?
Ground.
No, it's the fan.
Wrong answer.
Fan motor. Fan.
Fan.
Oh.
Okay, please be very careful about that, because for some reason, okay, when I toss that question out, always somebody is going to say ground. It's too easy to think green as ground. But the minute you go to low voltage, it's no longer ground. Okay? So please be very careful about that. Green in line voltage circuits is ground. But the minute you go to low voltage, it could be something else. Okay? So just be very careful about that. That question will show up on your final worded about 3 different ways, okay? So just be very careful. And it's a good job interview question. I guarantee it's a good job interview question. Okay, neutral. It's a conductor connected to the center tap of the transformer, and I'll explain that in a few minutes, and to ground. Okay? It's never fused. It's not always equal to ground, but it really should be close. It is a current carrying leg when it is energized. It's taking that current back to that ground, to that bonding, we call it, in the breaker panel. Okay, and I'm not going to explain this in the exact same way that the electrical instructors explain it. They go much deeper into this as electricians. But it is basically, it is your return to the breaker panel. Okay, because it completes the circuit. Do not ever trust neutral as not being energized. Okay, let me repeat that again, and this is so important. Do not ever trust neutral as not being energized unless you have tested it. Okay, how are you going to check to see if neutral is energized? Anybody, how are you going to check to see if neutral is energized?
Well, I guess if you have power.
What are you going to use to check it? Where are you going to check it from and to?
A voltmeter.
Okay, you're going to use your voltmeter. How are you going to check it?
Neutral to ground?
Neutral to ground. That's exactly what you're going to do. Okay, you're going to check neutral to ground. Now, again, the reason I stress this so heavily is in a commercial building, especially in our shops, okay, neutral can be energized. You've got to be very careful, okay? When you're working in shop, do you always trust the person who's working next to you?
No.
Okay, how about the electricians who are working in the next shop? Do you trust them?
Nope, trust nobody.
That's my point. Always check on your own. Okay, it's important. You can get really badly zapped by neutral if it's not connected properly, okay? People wire things wrong a lot of times, especially when you're learning. We expect it. Okay, equipment ground is otherwise known as an earth ground when you're looking at the equipment. Frame ground, earth ground, equipment ground, basically the same thing. It is the conductor to the equipment case and then ground. If it has a metal case, we ground it. Why do I ground especially equipment outside? Why do I want to ground it? Oh, why do I want to ground equipment that's outside?
Because of moisture.
Lightning.
Lightning. Why else do I want to ground equipment that's outside? There's two reasons. You got one, lightning.
Water.
Static electricity caused with wind.
Almost $18 million coming off of the...
What about, let me ask you a question, with those of you who have kids or younger siblings running around, or dogs, if there's a fault in the equipment, do you want them to touch that case that might be energized?
No. Kids. You don't want them to touch anything.
In all seriousness, no, this is one of the reasons. You have that condenser sitting outside sometimes in your fenced-in yard where you have either kids or pets running around. Okay, if a wire comes loose or if something shakes loose and is suddenly touching the case of the equipment, you don't want that equipment to be hot. Okay, you want that case to actually ground out to earth so we blow the breaker. Okay, ductwork the same way. If you have a furnace or air handler in your basement or attic, basement is where this is more important, and something shakes loose in there, some wire gets touching to the case, it happens. Do you want the entire ductwork in your house, everything that's metal going in through your house into your floors and coming up where people can walk on it? Do you want that to be energized? No. So equipment grounds are very, very important. Okay, the sine wave. I've talked about this a number of times. It's a chart representation of AC current, alternating current. When you look at a sine wave, the term alteration is 180 degrees of that sine wave. A cycle is two alterations, and I'll show this to you in a minute on a chart. Cycle is two alterations. It's 360 degrees of the sine wave. The frequency is the number of complete cycles in 1 second. Hertz is the measurement of frequency. In the United States, actually pretty much North America, the power frequency is 60 hertz, 60 cycles per second. Anybody know what it is in Europe?
50.
50. Okay, in Europe it's 50. Why do I care about what the frequency in Europe is, since I'm working in air conditioning in the United States? Why do I care?
In case you come across an appliance that's accustomed to 50 hertz rather than 60?
Believe it or not, it happens, okay? Especially when we're talking about ductless split systems, okay? You're ordering ductless splits. You as an HVAC technician or contractor are going to get these things from your supply house. You count on them being 60 hertz. You count on them being set up for the United States. What about happy homeowner who decides to buy the piece of equipment cheaper on eBay or Amazon and then calls you to come and install it? Do you know where that equipment came from?
Probably China.
No.
Well, probably China, okay? Yeah, that's probably where all equipment is coming from these days. But the reality is you don't know if it was manufactured to be used in the U.S. or in Europe. It happens frequently. So you got to remember to look at that label and say, wait a sec, I can't install this. This piece of equipment is set up to work on 50 hertz. It's not a system that can be installed in the United States. Okay, and that's going to happen to you. Okay, even probably before you graduate from school, one of your family members is going to hit you up and want you to install their air conditioning they bought on eBay. Okay, happens to somebody in every class it happens to. Okay, so 60 hertz is US, 50 hertz is Europe. Sometimes there's a switch on a circuit board. There's a little dip switch or a pin that you can change the jumper on to go from one to the other, but you got to go find it sometimes. Not an easy thing to find because they don't want you to find it. The phase, it's the number of currents operating with at a different time interval in the circuit. Now, yesterday, somebody did ask me about, and I forget if it was on this call or if it was on the other call, asked me about when I'm showing voltage, am I showing peak voltage or am I showing effective voltage? Okay, peak voltage is the voltage at the 90-degree point in the sine wave. Okay, that's my highest voltage. The effective voltage is what your meter reads, which is 0.707 times the peak voltage. In other words, it's slightly less than what the actual peak voltage is. Again, somebody mentioned this yesterday. I didn't really want to go there yesterday, but your meter is reading effective voltage. For lack of better terms, that's usable voltage. What the power is actually giving is slightly higher. Does anybody have any questions on that?
Yeah, how did you get 90 volts?
You're not getting 90 volts. It's at the 90-degree point. So if I have my sine wave, we have 0. Then we have 90. Okay? It's at the peaks.
So what would that actually, at 0.707, what would that actually be, you know?
Well, if I'm let me... Okay, if you have a calculator handy, which I can't pull up on my screen right now, okay, take 120 times 1.3. 120 times what was that?
156.
Yeah. Now take 156 times 0.707.
110.292.
Yeah, I mean, again, I'm doing, again, that 707 when I had you do the first number. But if you're getting 156 peak voltage, okay, which you're not measuring on your meter, we're coming down to about 110. Somewhat makes sense?
Yeah. And this is just another question I had that may or may not pertain. Is the ugly book something practical to have?
I've played around with that a number of times. For a while there, I used to have it. We used to actually have it as a part of our book collection. I know Electrical loves it. I honestly don't know. It's one of these, I like the book. I think it has a lot of awesome formulas in it. Okay, it has a lot of awesome material in it. But I'm going to later, make a note to myself. I want to post something that I think would be more valuable for you guys to have. Okay, Ugly Book is awesome. If you want to get it, get it. But there's another guide that is more HVAC related that I think would be a probably better choice for you guys. And I'll post a link to it. And again, when I post these helpful links, I need everybody to understand I'm not advertising these products. It's just nice stuff that I found along the way.
Right.
Does that answer the question? I mean, I really don't have a direct on that Uglies book because part of me says it's awesome, but part of me says it might be too much.
Just a guy I know, like a friend of mine is a master electrician, and he recommended one.
Oh yeah, yeah. For the electricians, I keep being told it's an awesome book. I'm actually the guy that I handle all the ebooks for the Institute. And I keep being told that that's an awesome book every time I do a book review on that program, on those programs. But I don't know if it's too much in depth for the HVAC.
Yeah.
So again, if you come across it, if you want to buy it, I think it's a good book. But there is something else that I would recommend buying if people want additional materials.
Yeah, I'd be interested in that.
Okay, I'll post a link later. Again, just to make it clear, I'm not advertising and I'm not saying that you have to have that product. So I'll post a link later.
All right, thank you.
Okay, so moving on. This is basically what we're talking about on the prior slides of the sine wave. Okay, we go from a positive to a negative with our neutral or zero in the center. Okay, this is basically effectively neutral. And again, if you've had electrical before, if you have electrical in the future as an electrician, you'll go much more into depth in this. But zero is in my center. We go from a positive to a negative, basically equivalent to north and south poles of a magnet. Okay, this complete cycle happens in 60 times per second. My 90-degree point, my 270-degree point. Those are my peaks. Okay? We come back through zero in the center. So we start a cycle at zero, we go to 90, we come back through zero, we go to negative 90 or 270, and then we come back up. In residential and light commercial, we would read on our meter. I'm not going to go into the peak voltage of the actual peaks because we can't read that. We would read roughly 120 there. We would read roughly 120 here. Is there a true positive and negative in any alternating current circuit?
No.
No. It happens so fast, every conductor is getting positive and negative alterations between 60 times a second. Okay? So we don't have a true positive and a negative. But what I do have, when I'm dealing with 120 volts, I do have a hot line. That's my L1 up at the top or at the bottom, depending on what side of the breaker panels it's coming off of. I do have an L1 and a neutral. White wire's normally neutral. So what lead should I usually be switching? Should it be L1 or should it be neutral? Both will break the path of current, but which lead should I be switching?
Neutral.
But neutral is 0 volts.
L1.
I should really be switching my hot lead, which is going to be your L1 or sometimes your L2. And again, I'll show you the insides of a breaker panel in a minute, and that will make more sense. But I should really be switching my hot lead. Why? Why should I not switch neutral? And think about from a safety perspective. Why should I not be switching neutral? It's okay to be wrong.
Possibly gain too much volts.
Yeah, but I'm more thinking safety. What if I switch neutral? Go ahead.
Get too hot?
I was going to say you're not going to want bulk equipment when it's not necessary.
If let's just say you have a room light, okay, or a fan, or something like that, and if you have switched off neutral, and you know you have neutral switched off, if you reach into there and do something internally in that circuit, Are you expecting to have line voltage there anymore?
Yeah, you still have voltage.
I still have voltage if I've only switched off neutral. So rather than having to path back to the breaker panel through neutral, what suddenly becomes the path?
You.
U. Okay, so we want to switch our current carrying conductors. Very important. I want to switch my current carrying conductors. Okay, this is a single phase current, what I'm looking at right now. This is single phase. This is three phase. Now, looking at this, this would be L1. That would be L2. That would be L3. This is time. So any split second in time, if I draw a line down through time, and if I look at my current, any split second in time, will I have any two legs in zero at one time?
No.
No. That is the major importance of three-phase. I will never have two legs of a three-phase current in zero at one time. So think about it. We started to talk about motors yesterday. Think back to what I was telling you about motors with the multiple windings and the reason for capacitors. Remember, a capacitor helps us shift the phase of the start winding so that we never have two windings without a magnet, without basically magnetism, okay? Because if our magnetism collapses when it goes through zero, which is a very simplified way of putting it, okay, will I ever have, if I have a three-phase motor, which I haven't drawn out for you yet, but if I have a motor with three windings, okay, I have a winding there, I have a winding there, I have a winding there. Those are windings, pretend. Okay, will I ever have two windings with 0 volts?
No.
Anybody? Will I ever have two windings with 0 volts?
No.
No.
No. So, a three-phase motor, do I need a capacitor?
No.
Yes.
No. Because this is automatically out of phase. Every one of these leads going to the motor. I have L1 there. I have L2 there. I have L3 there. A three-phase motor, I don't need a capacitor because I already have this phase shift going on. Now, we're going to go much more deeper into three-phase motors, but there's a couple things I want to tell you about three-phase motors. They have three hot legs, L1, L2, and L3. Okay? They all have the same resistance. We do not have a start and a run winding. Three-phase motors, each leg of the three-phase motor will have the identical resistance.
Are those like the motors that are in cooling towers?
Well, it depends if you can have a motor on a three-phase circuit where you're only using L1 and L2, so be careful about that.
But
Okay.
in general, will a three-phase motor draw more current?
Actually, for the work that a three-phase motor is doing, remember, it's all based on the work being done, okay? So, but for the work a three-phase motor is doing, it actually draws much less current than a single-phase motor.
So it's more
So if
efficient.
I have a motor driving a compressor, a big compressor, not a little tiny thing that you see in somebody's house, okay? We're going 5 tons and up of equipment.
Yeah.
So if I have a motor driving a compressor, that's a single-phase motor with capacitor, my amperage on that single-phase motor under full load is going to be, let's just toss a number out there, okay? I'm just tossing a number. Let's say it's running at 14 amps. If I take that 5-ton compressor and replace it with a 3-phase 5-ton compressor, I could effectively cut my amperage in half. Okay, and again, it all has to do with that I now have an extra powered leg of this circuit. Okay, the 3-phase motors can do much more work at a lower amperage than the single phase. So the question comes up is, why don't we supply 3-phase current to every single building in this country? Anybody?
More costly.
That's what it comes down to. I know I have somebody on this call who's had electrical already. From the street side of a 3-phase circuit, what do I have to have on the pole outside the building?
You have to have a transformer.
Not just one transformer, right?
Yeah, 3.
I have to have 3. So if you look outside your house, either buried in the ground or on a pole close by, how many transformers do you have? Right now, on single phase, how many transformers do you have?
I have 1.
Yeah, single phase power. You only have to have 1 transformer coming off the street. You have one main line carrying voltage at the top of the pole. Big cost difference for single phase versus 3-phase from the power company. Okay? Would it be great if they had 3-phase current coming into every building? Oh yeah. We could eliminate so many parts out of our air conditioning systems, and quite frankly, we would use a lot less power. Okay, but I'm not 100% sure the power company cares about us using less power. Okay, so single-phase power versus 3-phase. Single-phase, we have 2 current-carrying conductors. For 120 volts, that's L1 and neutral. Now, again, neutral is weird. It really should, the effective voltage should be 0, but the bottom line is it does become part of the circuit. 208, 230 should also read 240, L1 and L2, single phase. Because you do see this at 240 as well, in residential primarily. This could be 240. Could it also be 250? Can you measure 250 on a residential circuit?
Yes.
Yes. Okay, the power company can go up to, I believe it's 10% over or under. Okay. Single phase, I can obtain it from a 3-phase circuit. We do this in commercial buildings all the time, including your campus building. We do this all the time. Okay, if I have L1, L2, and L3, I can use L1 and L2 by themselves. And with a little bit of magic, I have single-phase current. I can create a neutral. Okay, and you have single-phase current. Okay, if I create a ground and go L1 to ground, I can have single-phase. That's way oversimplified. But I can create single-phase from a 3-phase circuit. This is the most important point from what we're dealing with in HVAC. Single-phase motors require a starting device. Okay, it's not only protect the start winding, but it's also to provide that additional the out of phase for the start winding. Okay, requires starting devices. 3-phase circuits has 3 conductors. Somebody's going to argue with me that it also has a neutral, okay, or a ground. Could be 4 sometimes if we have a neutral. We don't often see a neutral. Unless you get to the lower, unless we're splitting that three-phase. Three-phase is used on commercial and industrial applications. Three-phase motors don't require any starting components. Three-phase power is very, very versatile, extremely versatile. I can do a lot with it. I can also create single-phase power. I can create different voltages. I can create lighting-only circuits with a higher voltage. There's a lot I can do with three-phase power. If it were available, it would be the best thing that could possibly happen to residential. But it's never going to happen because of cost. Okay, so again, single phase, three phase. Now, power distribution is important, okay, because remember, we have to have a source. So where you look at the power, different people look at sources in different ways. Okay, but from the power plant, the power enters a substation and the voltage is stepped up. Okay, from the substation, it's sent across the country. Then it gets to your local substation and it steps voltage down. Okay? Sometimes there's another one along the way that it retransmits, so it steps it up. So any time I step voltage up, what happens to the amperage? If I take a lower voltage and put it up, what happens to the amperage?
The amperage goes down.
Amperage goes down. So when I step that voltage down as it comes into the local distribution network, what happens to the amperage?
It goes up.
Yeah. Okay, so our high voltage lines that you see on the big tall towers, in the grand scheme of things, have extremely high voltage, but might have a lower amperage. It actually might be lower than the amperage that's in your house, but the very high voltage.
What always amazed me about these high transformers is that they're completely steel and they're grounded. So you can touch them and not...
Yeah, but now what is up on them that's so important to make that? What's on every single one of these transmission towers?
Those insulating socket things. I don't know, were they porcelain or glass?
Yeah, glass or porcelain, and now sometimes some material. It's a sort of a plasticky material that they use. So there's a ton of insulation up there, and those lines are specific distances apart based on the voltage.
Is there a magnetic field because the voltage is so high, like between the lines?
Oh, there's very definitely a magnetic field between the lines, to the point that the people servicing these towers actually put themselves into a suit. It's sort of a gridded, it's sort of a metallic suit that they ground themselves first to they're servicing it from a helicopter platform. And they get close to the lines with the helicopter, they then ground, they actually connect the helicopter with a pole into the line. Then the person servicing these towers and these lines get out of the helicopter, connects themselves into the circuit, and so on and so forth. There's a big procedure because of the range of the magnetism and the range of the power and the possibility of arc flash.
Jeez.
Okay, there was I forget what channel it was on. I think it might have been the Science Channel, where they actually did a full there was an awesome show on these people servicing these high voltage lines. One of my neighbors actually flies a helicopter that services these high voltage lines. Okay, and this is done frequently. You got to get up and service the wires, but you can't take the power off these lines. They're always powered. So it's a real trip, apparently, to do this whole service procedure.
Yeah, it's probably very expensive, too. Whoever's doing that's making a lot of money.
It's very risky, too. Sometimes you get paid based on risk. Now, in terms of magnetism, I'm sure you've seen the show someplace where when they first put up high voltage transmission wires, and they build new lines and everything, everyone in the path of these wires cries about the fact that they can stand in their backyard and hold a fluorescent light bulb, and sometimes it powers up on a damp day. So yeah, there's a lot of electricity energy around there, not only with magnetism, but EMF. Is it harmful? No one really knows.
Talking about equipment grounding, I know, because I put fence at a power plant in Maryland, and we had to ground our machine every time we moved.
Oh yeah, because of the electricity in the air.
Mm-hmm.
I can see that.
Right, we had to ground our machine every time we moved.
I serviced a power plant in Charlton, Massachusetts, where anytime I went in there, I had to watch a video on how to protect myself against stray power. You had to do it every single time you went in that place. You had to go through a safety briefing. You had to ground everything you touched. You had to be grounded. Even if you were working on a relay in an air conditioning system, we had to ground ourselves. They take that pretty seriously. But back to the diagram here. So your power generating plant might only be putting out 13,800 volts only. You go through a step-up transformer substation. Again, the higher the voltage, the longer the distance I can run this power without line loss. Okay, line loss comes up when we have lower amperages or higher amperages and lower voltages. So our transmission towers could be 500,000 volts. Okay, that could be it could be higher now. Okay, they keep upping these voltages because they're learning how to make wiring that handles the higher voltages. Then these power distribution has step-down transformers, substations all over the place. Then this is your street wiring. Okay, this is on the poles in your local distribution network. Then it could go through a transformer before it goes into a building. Okay, this is more for residential and more for mixed-use area. We have another substation at the end of this transmission line. Our power on our street is about 13,800 volts. Again, notice this number. It's almost the same as what we created. Okay, we go along here and the poles at the houses, or could be in the ground, at the different buildings, step this down to whatever you need it. Okay, schools, stores, commercial, homes, we always step down to 220 legs that are 180 degree out of phase, so we get our 240 volts. That's power distribution. Okay, out on the street, coming to the commercial buildings, you'll most likely have three hot wires on the pole. Okay, once you get into your residential distribution system, you'll have one hot and one neutral, which is grounded. Okay, and the transformer creates the two legs coming into your house. It's much easier to run that single line. Okay, they run a single line plus a neutral or a ground. And then your transformer splits that apart. The neutral in your house is actually connected to the neutral on the pole and to ground. Okay, so there's a full path. Okay, this is why if the pole gets hit with lightning, if you take a lightning strike on the wires, it can actually travel through neutral if things aren't grounded properly. Happens quite a lot. Grounds go bad over time. People pull grounding straps. People pull grounding rods. It happens. So that's why I say never trust neutral. You do not know what is grounded and what is not, so you always have to test it. Once you come in from your street, you have a hot leg. Okay, up at the top, you have your basic neutral. Okay, so you have one hot wire. This is the one at the top of the pole. You have one neutral. That's also grounded. Okay, that's an earth ground. That neutral comes into your breaker panel. okay, and goes to a neutral bar. That's on one side of your panel. Notice it's also grounded. You see how many times this neutral is grounded? It also comes off the center tap of the transformer. That's why this is not necessarily, I can't call it a dead leg, but it is the center of everything. Okay, it's grounded at the house. It's grounded in the power company's world. It's the center tap of the transformer. Okay? Neutral is important. This transformer on the street, the primary side, 13,000 volts. The secondary side, L2 is a hot leg. L1 is a hot leg. Okay, L1 to L2 gives me my 240. L1 to neutral gives me my 120. L2 to neutral gives me my 120. It's the difference in potential between L1 and L2 that gives me my 240. Somebody sent me an email question on this the other day. Okay? If I have L1 and L2 labeled on any power supply, that's a 240 volt if it's in a residential. If I have L1 and neutral, or just L and neutral, it's 120. In your breaker panel, you have 2 rows of breakers. Depending on which side of the breaker panel that breaker's on, and I'm talking the single pole breakers, okay, where it's a single switch. Depending on which side of that breaker panel is on, it's either connected to the L1 or the L2. A good electrician, when they set up your breaker panel, balanced the loads. In other words, you don't want all of your appliances on L2. You don't want all of your lights on L1. Okay, so they balance the loads out. So half your kitchen appliances would be on L1, half of them on L2. Okay, a double pole breaker, where it has 2 breakers, basically it's a larger, wider breaker. It has 2 breakers, and usually the handles are connected with a piece of plastic, or that you can't turn one on and one off by itself. A double pole breaker goes across both lines. It has one, it's capturing L1 and L2. If you walk into a building and see a 3-pole breaker any place, what type of circuit do you have?
A 3-phase?
A 3-phase circuit. Okay, you will not see a triple pole breaker any place other than a 3-phase circuit.
What would that be used for? Why would you need that? Like, for what kind of, what would that be powering?
If I have a 3-phase circuit and a 3-phase breaker on a commercial building or light industrial, could be powering a rooftop unit, could be powering a chiller. Basically anything that has a 3-phase motor in it. Okay, heavy commercial chillers, supermarket rack systems. Those of you who are on the York campus, okay, you guys have a supermarket rack system in your shop that's 3-phase, that has a 3-phase breaker on it. Those of you guys in Hamden and Waterbury, you guys have 3-phase in your shop. Okay? Those of you in Chicopee, I think the electrical shop has 3-phase in it. Okay? And a lot of the rooftop equipment in all of your buildings, the rooftop building cooling systems are all 3-phase. So all of that will have 3-phase breakers. Any other questions on this diagram? Because even though you're not servicing any of this, it's still important to realize how this is all connected. Okay, I have a question. This ground, the ground in your house, or in most buildings in your area, what's that grounded to?
Outside, right?
The actual ground.
Ground.
Where is that ground? And outside is one possibility. Where else will you see that ground connected to?
Basement.
What exactly in the basement?
In the yard.
Zach, what exactly in the basement?
Isn't it called a spike?
Yeah, I'm not 100% sure. It just sounded good. Sounded like the right answer.
Well, it actually was one of the right answers. It was the one I'm looking for. And by the way, everyone else is saying spike in the ground is correct as well. Okay, they're connected to the water line. A lot of times, if you have copper water line, they're connected to that main water line coming into your house. Okay, now, that causes problems. What happens when the city comes along and decides to replace that meter outside with a PVC pipe and a meter with PVC piping? What happens to your ground?
It goes away.
Yeah. So that's what I'm saying. Some of this is out of your control, and the guy who's replacing that pipe in the yard with a PVC pipe or a plastic pipe doesn't know that your electrical circuit is grounded to that pipe. Okay, so you could all of a sudden no longer have a ground. Bad things happen.
Speaking of grounds,
and you won't find out. What was that?
I said, just speaking of grounds, our barn growing up on our farm had all these, I don't know what you can call them. They were spikes across the top to...
Yeah, lightning arresters.
Yeah, lightning rod, yeah. And we had big cables that went down the side into the ground. And I've seen lightning strike that because the roof was metal. It was a very large barn. And, yep. I mean, you can see the power arcing, like the whole thing going, but that went right into the ground.
Yeah.
I spent my high school years way back in the dark ages. I grew up on a dairy farm, and not having a ground was a major problem. Okay, if our ground went bad, all of a sudden on the farm, we had stray voltage, it's called. It's one of the worst things that can possibly happen to dairy cows, is having stray voltage, because it gets in the water dishes and all of a sudden they're afraid to drink. So grounding is extremely, extremely important as like in everything. That's why I spend so much time on this idea. Okay, so voltage enters the building through a cable, the weatherhead, the conduit, the meter box, and the panel box. HVAC technicians are not allowed to touch anything in the breaker panels. Okay, officially, and I need to stress this. You guys, the licensing, every bit of insurance you carry as an HVAC technician does not let you do anything in the breaker panels. Okay? No state allows an HVAC technician to do anything in the breaker panels. Okay? The breaker panel consists of fuses or breakers, now breakers. It has a main disconnect either in the panel or outside under the meter. It has individual circuit breakers. The main breaker has a rating for each line. Okay? So again, this is our system. Once we get in the house, we have our main breaker, and then we have individual breakers. This is all sized by an electrician, whoever installed the job. They have a whole course in our electrical program on sizing. Okay, so I'm not even going anywhere near that. We have to, as HVAC technicians, trust that the power we are being given is clean and the breakers before that are sized. If you find a problem in a breaker panel, that goes to an electrician. The branch load, that's the loads coming off of here, the wires going out to the appliances, plugs, outlets, whatever, may not exceed the rating of each branch circuit. Everything is wired in parallel. Okay, we don't want one load to go out and take out the entire circuit, so everything we do is wired in parallel up to where we deal with control circuits and circuits inside equipment. Each branch load may not exceed the load of the main breaker. So if I come back to this page here, if I have a 200 amp main breaker, my loads on the branches cannot go over 200 amps. It's not fun when a main breaker blows. I've seen it happen too many times. Okay? It's not a good thing to have happen. And you as a technician, if you install a piece of equipment wrong, you can actually blow that main breaker. Okay? They're not easy to reset either.
So if that happens, then an electrician has to come reset the breaker.
No, you can reset the breaker if you find the problem, you blew the main breaker. You're allowed to reset the breakers. You're not allowed to do any of the, like, you can't take the panel off the cover of the box. You're not allowed to do any wiring in the box. If you need to reset a breaker, that's all you. You can reset it because our homeowners are allowed to reset breakers. Okay, but if you need to take the cover off the box, if you need to go into the box to do anything, if you want to connect a new appliance into the box, that's legally, that's an electrician.
Can you turn the power off if you needed to do something with a system? You can turn the power off.
Oh yeah, you have to. Yeah, you're allowed to use any of the switching of the breaker. But again, you can't legally, you can't remove that panel cover and do anything inside the panel. Am I saying that properly, or am I still causing...
Yeah, I understand.
Okay. Now, the reality is, do we all do it from occasion? Yeah. But the legality is you cannot go into that breaker. Be careful, because arc flash is a real thing. Okay, my local electrical inspector has been out of work for probably 4 months now because he pulled the cover off a breaker panel and the electrician didn't have a main feed. This main feed wasn't tied down properly to the main breaker. It wasn't clamped down. He pulled the cover off the panel, the main feed popped out, touched the metal, and he got nailed with arc flash. That was the inspector. Probably not a good idea to try to kill the inspector. But it happens. Okay. Again, branch loads may not exceed the main load. Neutral comes from the center tap of the transformer. Ground should be connected to the grounding rod, not to a water pipe. Remember what I said, water pipes change over time. Very often in older construction, you will see ground connected to a water pipe in the basement. You can follow the ground wire out of the box and it's connected to a copper water pipe. That's not a good idea. Okay? Doesn't work too well. Branch wire color codes, most of the time it's black, white, and red. As soon as you have three-phase, you'll have blue. Green or bare wire on line voltage is ground. Any questions on that? Okay.
How would you test? What would you do to make sure that the green is like ground? How would you test that?
That is a tough call. If I'm at the breaker panel or right there to the breaker panel, I'm going to follow the wire. If I'm out at a job site, like if I'm on a piece of outdoor equipment, okay, I am going to take one of my hot legs with my meter. I'm going to put one probe on my hot leg. I'm going to put the other probe on the ground wire. What should I get?
Nothing.
Wrong answer. My meter, I should get part of source because my meter is measuring a difference of potential. If my ground is truly grounded, okay, so from L1 to ground, I should get roughly 120 volts. From L2 to ground, I should get roughly 120 volts. If I get zero,
then it's not ground.
Then I have a problem with my ground. I'm going to be very concerned. What's another way I can test ground? There's one other way I can test ground and I can get somewhat close. What about resistance? Resistance, I can test ground if I know what I'm looking for. I can go with an ohm meter from ground to ground. Okay, if I'm outside, I can go with an ohm meter from the ground terminal of the equipment to earth. Okay, especially if it's damp. I can go, if I'm near a furnace, I can go from the ground terminal or the case of the furnace to a water pipe close by, if it's metal water pipe. Okay? So you have ways of testing ground, but I really like the voltage method the best. Go from one of the lines to ground. I have a tendency to check voltage on my equipment frame, especially if as I've told you guys before, I do a lot of insurance inspections, like with lightning storms and hurricanes and stuff like that. I have a tendency to always check the voltage between the case of the equipment and earth ground before I touch it. Okay? I will take my meter. Before I touch that equipment outside, I'll put one lead on the equipment. I'll put one lead on earth ground before I touch that equipment. Why do I do that?
So you don't get shocked?
Yeah. There's too many instances I've come across. I learned that the hard way. Thankfully, it wasn't high voltage. But I suddenly realized that as I'm in some of these, especially when we're dealing with hurricane areas, I was in Panama City Beach after the most recent hurricane, and I touched a piece of equipment, and I got zapped, and I suddenly realized that part of the grounding, part of the neutral is on the power company's side. Well, if they have lines down all over the place, if they don't have good grounding, if the neutrals have all been ripped apart, I can't trust the power company. I need to make sure that I know that there's no voltage on the equipment. So again, it's important to check because sometimes you learn the hard way. Sometimes you learn the hard way in a way that you don't get killed, but it's still an eye opener. So that is basically power distribution. Okay, I want to talk briefly about some single phase. This is very short, but just to repeat a few things we've talked about single phase power, because for most of you, you guys are not going to go into commercial as soon as you graduate from school. You're going to do your time in residential, which is not a bad thing, and then you'll move slowly into commercial. Okay, so again, single phase, 240 volts, 60 hertz. It's what we supply to residences. We've talked about the breaker panel before, and we'll talk about it again. Breaker panel is supplied with 2 hot legs and a neutral from the transformer on the street. The hot legs are black and red. Neutral is white. The circuits from one hot leg to another, from L1 to L2, will give you 240 volts. Neutral is not used when wiring a 240 volt load. So again, this is our circuit. Okay, L1 might be on one side, L2 might be on the other side. Okay, we have neutral in the center. Neutral's weird because it's not only the center point of the transformer, but it's also grounded in numerous different places, or it should be. 240 devices in residential, dryers, stoves, air conditioning units, air handlers, some window AC units, depending on what the plug looks like. Okay, if it doesn't fit into a standard outlet, it either is high amperage or higher voltage. Okay, there's different plug arrangements for different appliances. 120 volt single phase comes from one hot leg to neutral. Your household outlets, your outlets next to your desk, your lighting, etc. If you go to another country overseas, are the outlets 120 volts?
No.
Has anybody traveled where you've been overseas?
Yes, no.
No. Yeah, they can be up in the 200 volts. We are one of the only countries, along with Canada and parts of Mexico, that have 120 volts at the outlets. Okay, most other countries have up in the 200. What was that?
So why is that?
It originally came down to safety. When they originally designed the electrical system in the United States, they were very, very concerned about safety, and they didn't want too much power going to the outlets. There was a real issue with safety. That's why they did it.
So which is safer? What the rest of the world uses or what we use?
I think what we use is actually safer, but now there's a question on efficiency. Which would be more efficient? For example, if you want to use electric, one of the tea kettles, one of the water boilers, or a toaster, or a fan, which is probably going to be more effective in terms of getting the job done?
The 200.
Yeah, the 200. I can have lower amperage with the higher voltage. So there's a real toss-up on it. Okay, don't have an easy answer on that one. But unfortunately, it's sort of what we're stuck with. Okay, again, breaker panel. Okay, and again, some books you see will say the 115. We don't get 115 volt current anymore. The power companies have most often raised the 115 volts to the 120 or 120 plus. 122, 123 is what I'm seeing these days. Again, they can drop the current and increase the voltage. Okay, and it makes it more effective, more efficient for the transformers and everything else that has line loss. Double pole breakers go across both L1 and neutral. In a perfect world, our loads are what we call balanced between the L1 and the L2. We don't put all the load on one or the other. Okay, breaker panels, they're supposed to be wired neatly. Okay, you'll have a neutral bus bar. You'll have a grounding bar. They are eventually bonded together. But all your neutrals will come into one place, so you have a whole bar with white wires. You'll have a whole bar with either green or bare copper wires. They are bonded together. Okay, eventually. There's knockouts for other circuits, but again, you as an HVAC technician, and I need to stress this, are not allowed to do anything inside the breaker panel. That's for your own safety. Okay? That's an electrician's territory. Now, do I occasionally have to pull a cover off a breaker panel and take a look inside the panel just to make sure something's wired right? Yeah. Am I supposed to? No. Your job comes from the disconnect or the connection to the equipment. That's where your licensing and your responsibility starts. That the equipment disconnect or the connection to the equipment. If I don't have voltage in, if my breaker's set properly, and if I don't have power or if I don't have clean power, that's an electrician.
Does sound play into this at all? Like, should you be conscious of sound? Like, if you can hear the current, electrical current, is that something that you should listen for? You can't hear electrical current in low current situations or unless you're really having a problem.
I am very conscious of sparking. If I hear anything, if I'm troubleshooting and I hear anything that sort of sounds like something sparking, I'm very conscious of it. If I hear anything that sort of, this is a tough one to explain, sort of is like a small zapping noise that's not really a spark, but more of sort of a, it's almost like a loose connection. For those of you who've been near electric fences, it's almost like an electric fence sound. I listen for that. Okay.
Because sometimes I've been around old electrical stuff and you hear like a hum.
I don't really use that for troubleshooting because that's sort of, anything that has high amperage pulls by design is going to have that. And honestly, over the noise of a motor, like if you're next to a compressor and that compressor's running, you're not going to hear that. Do I listen to it in transformers and equipment? Yeah. If I have humming in a transformer, like a 240 to a 24 volt or a 120 to a 24 volt, I'm going to start looking at that transformer as a possible problem. Stuff should be silent that doesn't have moving parts. Don't know if that answers your question, Dylan.
Yeah, it does.
Okay. So do I notice noise? Yeah. Do I notice vibration when I'm dealing with mechanical? Oh, yeah. All of this stuff, I don't know. Over time, there's certain things you start looking at. Okay. Not going to spend much time on that one. So single-phase residential power distribution. Does anybody have any questions? Okay, does anybody have any questions on assignments that were due other than today's? Very, very important on today's assignment. Okay, you have a question. It's an assignment. It's not a discussion board. I want to know what you individually know. I want you to give me as best of a description as you can give me. I'm not going to give you the answers on this call because there's more than one answer. Okay? I basically said, oh, the wrong course. Hang on. There we go. That's yours. Okay, I basically gave you a whole bunch of pictures in here. I want you to use your power of observation. And I want you to find everything you can possibly find that does not look right in this piece of equipment. We're going to talk about this probably on Monday. This is starting to look at our troubleshooting side of things. Okay, there's a lot of things here that are not right. Don't say them on this call if you've already spotted some. But there's a lot of things here that are not right. This just happens to be an actual piece of equipment I saw yesterday evening. Okay? Believe it or not, it was still running.
That just looks confusing.
Take a close look at it. It looks confusing, but believe it or not, we've talked about just about every component in here already. But there's some things, I just want you, again, there's no right or wrong answer other than not trying. Okay? There's some things in here when you look. What was that?
I said, how many should we find? I know you're not going to give us the answer, but is there like at least 10 things wrong with these pictures?
Things that we've already talked about or things that are so obvious, I think there's 4 or 5 things that you guys can find.
Okay.
And above all, I'm going to, it was still running.
How?
That's a fire hazard.
I'll go more into that after this assignment's done, okay? I don't want to give too much because, guys, this is the stuff you're going to find, okay? For the rest of the courses that I'm with you guys with in this air conditioning course, in this air conditioning term, I am going to start showing pictures of stuff that I have found in the field, okay? And part of our discussions are going to be what's wrong with this picture. I think it's one of the best things I can do in helping you guys learn air conditioning is to show you what's wrong along with what's right. Okay, so when you look at this picture, and there's something else that I've told you quite a lot, okay, people, technicians, and everybody should be proud of their workmanship. I've said this before regarding your assignment. I'm not saying this now because of what you're about to do, but I'm saying you this when you look at a piece of equipment, when you look at what someone has done, be proud. They should be proud of their workmanship, and it should have been done right. Okay, so again, there is no right or wrong answer with the exception of not trying. There are 4 or 5 things that you guys can identify that there's a problem here. Okay, and it may not be just what we talked about in our lecture, but you guys have also done some reading as well. Okay, so again, this is not a discussion board assignment. Your answer comes to me. Okay, we'll go over it a little bit on Monday. As I said at the start of this call, please, please, please look for my announcement for what you guys are doing tomorrow. We do not have an online session tomorrow. I'm going to have a few videos for you to watch. I'm going to have some schematics for you to do. There may be a quiz out there, okay, but please look for my announcement. Everybody knows where the announcements are in Canvas. I do one every single day. But there will not be an online session tomorrow.
Hey, quiz.
Questions?
Yes, I have a question. Do we have to submit the schematics that are in-class schematics?
The ones that I put up there that basically say in-class, no. I went over most of those yesterday, and those are more for you to practice with.
Okay.
Do we have a schematic for today at all?
No, you don't. I decided to do this troubleshooting thing instead.
Okay, no problem.
You will have one tomorrow.
Okay, I'll look for it. Thank you.
Quiz.
Yes.
The past schematics that are due already. Like I sent you mine yesterday on email. I don't know if you got it.
Yeah, I do. Guys, this is actually a very important point. Thank you for asking me that question. When you send me an email, I don't get to them right away, but as I sit down every evening and do grading. I do get to them, and I do take care of them. I may not respond, but you should see a difference on your grading. Okay, if you don't see something within...
On my grading, it still said missing.
It might say missing, but it should have a grade next to it if I got it.
Okay, I got one to send you today too. So.
Okay, now if they're late, I'm going to take points.
Yeah, I know.
Okay.
Thank you.
Okay, you guys all have a great day. I'll talk to you on Monday and look for my announcement for tomorrow.
Thank you, sir. Have a great weekend.
Thank you. Have a good